So on your calculator next to the number 4 is base 10. That is the common log. Base 10 number system probably makes sense that it's common. We also use the base E a lot in mathematics, so it also gets a special button on the calculator. Those are really the only two that we're going to use the calculator for, base 10 or base E. All of these properties are the same properties you saw before in base 10. If it makes more sense to write them, you can write them out, like log base E of 1 is equal to 0. But we just shorthand notation ln for natural log. I don't know why it's not NL, but ln. Maybe logarithm natural. I don't know. So log base E is really what all of these rules are suggesting. So evaluate the following. As I lecture, sometimes I'll switch into log base E form just to rewrite it for you guys. You don't have to do that. It's just so you can visually see it. So this is one of those times I do that. I say instead of the ln, I'm going to call it log base E. So we're taking a logarithm of an exponential function. Both bases are the same, right? Base E logarithm, base E exponential. When they undo each other, what's going to happen? It's equal to 5. Now, if you don't see that, you might set this thing equal to W, right? If you don't remember the property of something, oh, I forget, so let's write W. Now take this, rewrite it back into exponential form quickly. Bases are always the same, so if it's log base E, base E, logarithms are always equal to the exponent, so what's your exponent? Log base E, so I take this base E and I write it here. Logarithms are always equal to the exponent, so W is my exponent. The only thing left is to write E to the 5th power. I'm telling you, the left-hand side is the same as the right-hand side by the equal sign. So they're both base E. What do you know about the exponents? So the missing number is 5. It's a lot easier if you understand the property. They undo each other, 5 is my answer. Chunga property, done. But if you have to go through the process of rewriting it, you can get there. What about B? 3. If you don't see that, you might so it's an exponential base E being raised to a logarithm of 3. So what you might do is pull this out and you would say ln or log base E. Does anybody know what that's equal to, this exponent? I'm writing the exponent off to the side. Does anybody know what that's equal to? Like if you said it's equal to W here. Log base E of 3 is equal to W, right? Does anybody know what W is? No, we don't know what W is, right? So now, here, come back down here. Gets a little circular, kind of like a Jedi mind trick. So let's say E to the ln of 3 is equal to W. So coming back to here, some of us would say, okay, well, I can rewrite this, right? I'm actually getting myself all confused myself today. If we don't know what it is, we could rewrite it and we could say, oh, well, this is logarithm form, right? And then when we write it in, or it's in exponential form, excuse me. When we write it in logarithm form, what would it look like? Log base E. Logarithms are always equal to the exponent, which I could also write as log base E of 3, and I can put my W there. When you take, hang on a second. When you take this exponential up here, I squiggled off to the side here and I said this exponential has an exponent that's ln of 3. So as I bring it over here, it's really log base E of 3 is equal to something. I'm not sure what ln of 3 stands for. That's what it looks like. I don't know. So now if I bring it down here a different route, I'm looking at it as a whole thing. Again, I set it equal to W like we've done before. If you rewrite this exponential into logarithmic form, E is your base, so I'm going to write log base E. Same as ln, so it's log base E. Logarithms are always equal to the exponent, so I took the exponent, ln of 3, and put it over there. I wrote it as log base E, though. So I took that exponent over there, and I put W there. What do you notice about the two logarithms? They're the same.
So W.
There's an equal sign in the middle, so what does this tell you? That W is 3. So some of these get a little bit circular to me, and you can kind of find yourself just spinning. But in both cases, A and B, to me, are using the Chunga property. One's a logarithm of an exponential, and both the log and the exponent or exponential are the same base. Here, it's an exponential being raised to a logarithm, where both bases are the same. So, I don't know. Practice those. Last one on this page. What does ln tell you about the base? ln is base E. Logarithm, now this is a logarithm, so this logarithm is equal to W, and logarithms are equal to the exponent. So when I write E to the W, it is supposed to be equal to 1 over E squared. So this one, as you look at it, we're saying E being raised to some power makes it flip into 1 over E. What's going to cause our base to flip 1 over negative? So I know my W is negative. Well, what's going to cause it to go from E to E squared? Negative 2. Grab your calculators, type those in just for practice. Showing somebody near you. I would round your answers when you do logarithms to 4 decimal places. Because as we get into future problems, like some of the applications about population growth, bank accounts, if you start rounding off like to only the first or second decimal place, and then you use that number in some interest rate problem, you are rounding off a significant amount. So at least 4 decimal places in these problems. What'd you get for ln of 2.3? What? 0.8329?
Yeah.
Natural log of 0.4? Negative 0.9163? Natural log of negative 4? Can't do that. Domain of a logarithm. Draw the picture of the logarithm graph in the air. What does it look like? It's following the y-axis up, and it goes way out to the right. So your basic logarithm graph is doing this. So what's the domain? 0 to infinity. Does it ever touch 0?
No.
No. So the basic rule is you take what's inside the logarithm and you set it greater than 0. Now this is very closely related to the square root. Domain problems that we do a square root. What do we do with the square root? We set greater than or equal to. Because with the square root graphs, the thing comes down to a dot. It actually touches the very left-hand point. But in logarithm graphs, it doesn't touch anything. It just follows that vertical asymptote. So anytime somebody asks you to do a domain of a logarithm, pull what's inside out greater than 0. I'll give you half credit if you do that on the domain problem. Subtract 3. So in this case, as long as x is greater than -3, it'll work. Because what happens when you plug -3 into this problem? 0. Can you take the logarithm of 0?
No.
No, it doesn't work. How about that one? This one, the notation is really like this. Okay, logarithms always have, I kind of refer to them as a firewall. There should always be parentheses. Logarithm of what are you doing? So it's really the absolute value inside the logarithm there. So what are you supposed to do? When is absolute value of x greater than 0? When is absolute value greater than 0?
At the time.
What?
Like at the time.
I didn't hear that. Sorry.
Only half the time.
Is that what you said? Half the time?
Yeah.
No, that's
Oh.
what I said.
Well, when we look at it, look at the graph. The graph is above.
0 to infinity.
What?
0 to infinity.
What about this stuff?
Negative infinity to 0.
Oh.
Negative infinity to
I've
infinity.
said it like 1,000 times.
Chris, don't pretend like you-
JP?
Is it negative infinity to infinity when x does not equal 0?
Right. Yeah.
Oh,
Is that what you said? Is that what you said?
That's what I
1,000
said.
times?
I said it.
So like 8.
The problem, the only issue we have, the absolute value graph is positive everywhere, is what we would say, right? But at that one particular dot, it's hitting 0. It's at 0, 0. So it's no longer greater than 0, strictly greater than 0. So there's only one spot where it fails. So you guys could write it negative infinity up to 0, 0 to infinity, all reals, such that x is not equal to 0, something to that effect. Everything works but 0. That's the domain in that problem.